coordinated for that?
Hey. Hello. Hi. We're just going to get right into it today because I'm spazzed out. I probably should sit down and bring myself together. But next Monday too. If it is not raining next Monday, we're going to start at 1 because of the eclipse. Because I am not going to not be outside when the eclipse happens. And I hope the same of you. So if the weather's nice, if there is no clouds, if it's cloudy, we're just going to meet. I'll let you know in the morning. I'm hoping we can see the eclipse. I think we get like 70 to 80% here. Mm-hmm. Is that about right? Yeah. So that's just an extraordinary thing. I was actually even going to cancel class on Monday and travel to the path of totality.
Oh yeah. Go to Texas.
No, I was going to go back to Illinois where my family is and then just travel to southern Illinois. But yeah, this is the last total eclipse that will pass through the U.S. in my life. I don't know about your all's, but I think there's like 70 years till the next one in the continental U.S.
I do not want to be alive for that long.
What? Well, by the time you're 90 or whatever, it'll be like lifespans. You'll be in like really good shape. There'll be some kind of like pill you can take, a cream you can rub on to stay young.
Mental shape? Yeah.
Yeah, and that too. You'll know some. Yeah, you'll be great. You'll be great. I don't want to be alive. I don't want to be 127. Probably. I don't think my wife wants me to be 127.
125.
Feeding me what?
You don't look a day over 125.
Oh, thanks. Yeah. I don't want my wife have to feed me rice pudding for like 50 years or anything like that. So, and then Wednesday of next week, again, if the weather's good, your class, you will have an assignment. You will have to come join me on Math in the Quad. I want to do this every year. And it's not next Wednesday, it's 2 Wednesdays. That's great. So in 2 Wednesdays, 2 weeks from today, Math on the Quad happens. And I will give you an assignment and you will come touch base with me out on the quad and say, hey, Dr. T, I'm here. Come look at my thing I did in chalk on the quad. So you will do some Diffie-Q on the quad. It's going to be awesome. I have colored chalk. It's going to be so much fun.
I don't want people critiquing my work.
Do I see, am I that critical?
No, but other people will see it if it's out there.
Just make it tiny.
Okay.
Half the people walking by, like last year I remember some guy said something like, oh, this is ridiculous. I shouldn't be forced to see all this traumatic math.
I don't want to put someone through that. See, I'm kind.
Just evilness. It's just a hateful person to say such a thing. Severely traumatized individual. So we've got due on Monday 3 face portraits, right? Give you a little time to work on those today for consultation. Hopefully you started. I won't make eye contact. As usual, I gotta close this door. Somebody's talking very loud. We are starting nonlinear stuff. Last time, or actually, first off, any questions on the face portraits?
On the third, it's not really factorable.
It's not fun, but use the quadratic formula.
Okay.
And then you can convert those eigenvalues to decimal if you'd like. And I would maybe do it in decimal form and get an approximate value.
Okay.
Because you get square root of 17 in the eigenvalue, and it's ugly. So I'm told by someone. So yeah, so the eigenvalue on the last one, you should find it, but just approximate it in a calculator and find the approximate eigenvalue. I wouldn't normally say that, but it doesn't really matter. Does that help, Lou?
Yeah.
Cool, awesome. All right, so last time we had x of t is the population of, I believe x was the rabbits. Is that true? Somebody check me on this, and then we had sheep in a limited space. There's sheep, and then there's the little rabbit. And the rabbit apparently is as big as the sheep. Was X the sheep? Thank you. That's all I needed, just a simple sanity check. And then we had these equations for how they interacted and how that affected the growth rates of each. And so X was, let's see, X is the rabbit, so there's more of those. So it's 3 minus X minus 2Y, because the sheep affect the rabbit population more. Is that correct? Yeah. Cool. And then y dot is y times 2 minus x minus y. Rate of growth of each population. We're also going to make another assumption here, which you wouldn't normally do when I said sketch a phase portrait, but they're populations. So we will assume everything takes place in the first quadrant of the plane. So we've got x, we've got y, and we're just in this first quadrant, like I said. So step one, and I'm going to outline how to analyze a nonlinear system by using this example instead of some arbitrary thing. So step one, so let's see, how to get a nonlinear phase portrait. Everything we've done so far is linear, and it's interesting, but now things get really wild. Interface portrait. Portrait. Cool. So step one is find the fixed points. Find the equilibria. And this is a little more complex. You haven't had to do this yet, because our fixed point in a linear system is always just the origin. Now it's not going to be. So what you have to do is, i.e., find all xy values where x dot equals 0 and y dot equals 0 simultaneously. So we want to find a place where growth stops for both populations. And here we're going to actually end up with multiple solutions to that. So let's do that. We'll come back to this because I think we've got a little bit to do here first. So set x dot equal to 0. And so we have this system. You're really not used to solving systems of nonlinear equations. It's a different beast. If this thing wasn't factored, I would definitely factor it. You want everything factored to get a really good understanding. So what I do is I take each piece separately. This one is true when x equals 0 or 3 minus x minus 2y equals 0. Right? So each part of the product is 0. And this one is 0 when y is 0 or 2 minus y, x minus y equals 0. Now, I have to take every combination of these things. So there's 2 ways the top one can be 0, and there's 2 ways the bottom one can be 0. So there are 4 equilibria that potentially exist if nothing repeats. So what I'm going to do is take one of these first conditions, assume x is 0, take that down here, and then look at each of these. So we have 4 equilibria. So let x equal 0. And then either y equals 0 or 2 minus 0 minus y equals 0. you see how I'm getting that? I'm just replacing x with 0 in the bottom equations, and this one doesn't have an x, but that one does. So this says y equals 0 or y equals 2. And then convert those into points. These are points in the plane. So I've got 0, 0, or 0, 2. So we found half our equilibrium. Let me stop. Just tell me if that makes sense. If there's any questions, yeah, we're good? Cool. So now, let 3 minus x minus 2y equals 0. Next. And the key thing is just make sure you have taken all the possibilities into account. So it's discrete math time. How many different combinations do I have? 2 pairs of shoes and 2 pairs of pants gives me 4 different outfits, you know, that kind of stuff. So I'm going to let this equal 0, and then I'm going to come down to the bottom and do the same thing again. Then either, and then either y equals 0, or, and I'm going to leave a little space here, or 2 minus x minus y equals 0. So things are starting to get a little more interesting. This one's not that interesting. So if y equals 0 and this is true, then that means 3 minus x minus 2 times 0 equals 0. I'm just plugging y equals 0 in. And so that says x equals 3. And let's just record that as an ordered pair, 3, 0. There's an equilibrium. I got one more. This is the interesting, complicated one. Because this one now says I have a system of equations. So this and 3 minus x minus 2y equals 0, I have to solve simultaneously. So let's do a little scratch work over here. So I've got 2 minus x minus y equals 0.
Wait. So you got 2 minus x minus y. Oh, okay, yeah.
You good?
Never mind.
It's okay, cool. No, I'm glad. No, it's all good. I want you with us, Lou. You're probably not used to seeing things like this. You know, it really just says x plus y equals 2. That probably feels better emotionally. And then the other one says 3 minus x minus 2y equals 0. And again, let's fall back on what feels soothing. What does each of those look like in the plane? What are the general shapes of each of these guys? If you graphed them out, they're lines, right? There's just lines in the plane. So they have an intersection, and what we need to do is find the intersection. Here's an easy way to do that. I'm going to subtract down and cancel the x's. So let's call that 1, let's call that 2. 1 minus 2, or 2 minus 1 avoids negatives, doesn't matter. 1 minus 2 cancels the x's, gives me negative y equals negative 1. In other words, y equals 1. If y equals 1, then I plug that in, plug into 1, plug y equals 1 into 1 to get x equals 1. And then what I've got is my final equilibria at 1, 1. So let me stop, let you get caught up. That's step 1. There's some good stuff that's going to happen today. Put this back over here. Stalling. How's this feel? We can do this. This is kind of the easy part, but if these equations get complicated, then things can be challenging. So if this hadn't been factored for you, you would want to have factored it. In other words, if you had been given that, I would factor it before I did any of this work. So, all right, if that's all cool, we have 4 equilibria. Let's actually record this over here. So we have 4 equilibria. We had 0, 0. We had 3, 0. We had 0, 2. And lastly, we had 1, 1. We'll make a picture shortly. There's a little bit more to do, and this involves some new theory that we haven't seen yet. And you may have seen somewhere, if you had Calc 3, you might have seen this. But it involves partial derivatives. Has anyone not heard or seen partial derivatives? Somewhere you've got like x's and y's and you're differentiating with respect to. We're good on that? And I'll explain it as we go through. So that was step 1. Step 2 is we're going to linearize the system. And this involves creating something. Since I have 2 equations and 2 variables, we're going to create what's called the Jacobian. Create the Jacobian matrix. And I'll put the general form here. It's going to depend on what x and y are. And it's a matrix. It's essentially a microscope. Derivatives are microscopes. I'll talk more about that in a second. Let me get this up here. But it is the first partial of f, and I'll tell you what f is in a minute with respect to x. First partial of f with respect to y. First partial of g with respect to x. First partial of g with respect to y. Now what the heck am I talking about? So those things, your system will look like this. It's just, the f is the expression for x dot, so this is f of xy for us, and the g is the expression for y dot. And I'm actually going to multiply these things back out to do this work, because it's just going to be a lot easier. So let's actually write that out here. This is 3x minus x squared minus 2xy. Otherwise, you have to use the product rule when you do the x derivative. That just seems like overkill. So all I've done is multiply these through to make derivative life easier. Highly recommend it. But you probably get them unfactored. Okay, so let's do these partials. So the partial of this with respect to x, this symbol here, that is del. The del symbol, it just means derivative, but it's used for partials in particular. It's like the dx dy, or dy dx. It's just that thing going on. A fancy version indicating there's multiple variables. So the partial of this with respect to x, hey, could you take a crack at that on your own and see how much you remember about taking partials? And then we'll go through it. And in fact, why don't you do all of these? Let's just do this. You don't have to listen. You can do your own stuff. Sometimes my del gets a little crazy. And it's every now it's just crazy for me to say Del because that's my wife's middle name and I call him that all the time. Such a beautiful name. Oops. yourself. And then we can talk if we need to talk. And you know I love to talk. So, anybody want me to talk that through?
Can you talk to just one of them, please?
Absolutely. So what we're going to do here, Trayson, is we've got these two variables, x and y. We're going to treat, when I do the derivative with respect to x, like this, I'm going to treat y just like it was a number. So the 3x, derivative of 3x with respect to x is 3. Derivative of x squared is 2x.
Okay.
And then this guy, the y is just goes along with the 2. Does that make sense?
Yeah.
Yeah, awesome. Good. Brandon, you good on that?
Yeah, I think so.
Are you sure? I'm happy to, you want me to walk through another one?
Yeah, walk through the second one, the partial of g over x.
G over x. Oh, awesome. So when I do g with respect to x, y now acts like a constant. So this might as well be 27. It goes to 0. So anything purely y doesn't change with respect to x. So this goes to 0. This goes to 0 because it has no x's in it. And then this thing here is like, if I asked you what's the derivative of negative 2x, you'd say negative 2. But really I just have a y there, and the y acts like the constant in front.
Got it.
Help?
Yep.
Awesome. Cool. So this is going to help us put together our Jacobian matrix. So our Jacobian, and then I would write this out. Use the notation to keep track of what has happened. Minus 2y, negative 2x. Oh wait, sorry. I should have put these across. This is my top row. And keep this rhythm in mind. So then this is minus y, and this is 2 minus x minus twice y. Stop. Just want to talk about derivatives in general. Every derivative is a microscope. It is a mathematical microscope that essentially allows us to zoom in on a region. So if I took this thing here, it looks all curvy, but when I start zooming in on it, that's the lens of the microscope. It eventually looks just like a line. I don't know Pokemon. I know Pokemon. I'm not a Pokemon savvy person. Is that like a Pokemon thing? Which one, the final one?
Like it.
Huh. Yeah, it's Pokemon.
Yeah.
But it essentially allows you to zoom in. So what do you do with the derivative? You find the equation of the tangent line, right? And the tangent line, so let's do that. So the tangent line right there, eventually, if you zoom in enough, the tangent line is indistinguishable from the curve itself. So tangent lines are just zoomed in versions of a curvy thing. And we turn something wild and curvy into something straight. We say things are differentiable if they end up looking like a line. Not everything is differentiable. If I had this curve and I started zooming in here, there's really no way I can get rid of the pointy. Zoom in again. Keeps just looking pointy. No matter how many times I zoom in, it's pointy. That is called non-differentiable. Non-differentiable things are sharp. They can never look like a line. And so when you take a derivative, if the derivative exists, it means things look flat when we're close up. No sharpness. Same thing here. This is a mathematical microscope onto the behavior of this thing at points. I'm just zooming in. And what we're gonna do, here's the overall scheme, we're about to do it. We're gonna take that Jacobian, we're gonna plug in each of these points and see what the microscope tells us about what's happening at each of these. We're gonna go take that matrix to the tau delta tau plane. We're gonna find the trace, the determinant, find where it falls in that relative to that parabola or that bottom region. We're gonna classify each of these based upon that, put them in the picture, try to connect the dots. I'll say that about 5 or 6 times, but that's the big flow for today. So let's do that. So step 2 is find the Jacobian. Step 3 is evaluate the Jacobian at each equilibria. At each fixed point from step 1. So we do that. Oh shit, I see people taking notes that never take notes. I must be saying something new. All right, so let's do that. So J at zip zip. X is 0, Y is 0, I've got 3, 0, 0, 2. Hey, tell me something. Take a look after you get caught up. What are the eigenvalues there? I heard it, what? 3, 2, right? Diagonal, read them right off the dang diagonal. Is that a source, a sink, a saddle? Source, outflowing. So at the origin, things are flowing out. It's pushing things into the system. So I know that's a source, but I could also grab the tau delta information and discern the same. But you can just read the eigenvalues right there. They're cake. Let's do this and then we'll get to that. So the next one, doesn't really matter what order. I'll go in the order of that list. 3, 0. Could you do this for me as well? Let's all go through and do this. Because frankly, I have to pee. And then I'll just put up step 4. I guess we have that recorded. Step 4 is classify each fixed point using the tau delta plane. I'll be right back. I think that's enough. I think that that'll keep you busy. you see me write up something that you disagree with, please let me know. No, there's said anything so far, so I'll take it. Yep. Pop. It was looking good. Okay, all right, I did it. Yay, congrats to me. And then I would go through these. You can look at these first three and know without tau delta. And you don't have to do that if it's obvious. What are the eigenvalues here?
-3 and -1.
Solid, just read it. It's a diagonal matrix. Got a 0 in the lower or the upper, lower left or upper right. What about here? -1 and -2. Just read them off the diagonal. There's a 0 in this pocket, so I can read the eigenvalues off the diagonal. Be careful, that 0 has to be down here or up here. If it's anywhere else, this game doesn't work. So what kind of, what is happening at this point? Sync. Two negative eigenvalues, both in incoming directions, are attractors. What about here, Lou? You were doing that one. You Lou?
What?
I was just asking what was going on here in terms of
Another sync.
sync. Cool. I was talking to Lou and then I changed it over, so you can be forgiven quite easily for all sorts of things, frankly. So for this one, look, we've got lambda equals 2, 3, lambda equals -3, -1, lambda equals -1, -2. This is a source. This is a sink. This is a sink. I didn't really need to go to the tau delta plane in the diagonal case. Now this one is a little more interesting. So what is happening at this equilibria that sits in the middle of that first quadrant? So we'll do tau is -2. It all comes down to this delta. If this delta is positive, I've got some sort of stable node or a stable spiral of some kind. But tau turns out to be -1. -1. So what do I have? Saddle. Bottom half plane. I'm in a Saddleville. So this is saddle. Cool. Let's start plotting. Step 4 is classify. We just did that. So use either the diagonal structure to exploit the ability to grab those eigenvalues. By the way, that works for any size matrix. If I gave you a big old matrix like this, even a 4x4, and I won't, but I wish I could. I'd like that very much. But we need a whole other semester to do this. The eigenvalues of whatever that original thing were are 3, -1, 2, and -5. Just read them right off. Even if there was a bunch of crap down here. So, all right, let's start plotting. Step 5 is put it together. And the final step, and I'll give you a couple pointers. Depending on how accurate you want this to be, you might want to find some vectors for your manifolds, the incoming and outgoing things. The semi-straight lines near the point. I almost put a right angle there. I don't know what I was thinking. I think I was thinking geometry for some reason. So, step 1, go to the plane, mark off each equilibrium. So let's see, let's get nice units here. 1, 2, 3. There's one there. That's my 3, 0. 0. Just add a third. Okay, there's my 0, 2. I've also got 0, 0. And then I've got 1, 1. Okay. I want to give you some other fun tips. If you have a diagonal matrix, this is a diagonal, this is triangular, that is diagonal. Let's just put a few little helpful hints. If the matrix is diagonal, what that means is there's non-zero stuff with zeros on either side of it. Like that thing. The eigenvalues are on the diagonal, and the eigenvectors are just the axes. So here, the eigenvectors are 1, 0, and 0, 1. And this would be for the, here, let's see here. This is like this, lambda 1, lambda 2. This would be the lambda 2 direction, and this would be the lambda 1 direction. Of course, it'd be helpful to have a lambda 1 there. That's a helpful thing, because that means down here at the 0, 0, my first equilibria, I know that my vectors are the axes. They're the coordinate axes. Everything okay, Lou? Stop me before you furrowing your brow.
Oh, sorry, I was just looking
No,
at
don't, no sorries. No, I'm-
diagonalized.
you're scaring me.
Just with the 1 and 2,
Yeah.
I was just checking it out. For myself.
Thank you. I appreciate that. Does it check out?
Um,
Now you got me worrying. So let's do it. So let's see. So let's do the 3, right?
Yeah.
So let's do lambda equals 3, and we're using this matrix. So I'm going to subtract that off the diagonals. And then I do xy equals 0. So the first equation doesn't give me any information, but the second one says y has to equal 0.
Yeah, I think you just.
I think I did it backwards.
Yeah, that's it.
Thank you. And actually, that's easier to remember. Is that? Yeah. Yeah. It's even easier to remember because it matches where the eigenvalue is in the matrix. It's just like a whole heuristically more pleasing thing. Cool. So the 3 corresponds to this direction. So I'm outflowing there, and it doesn't really matter, but we'll put lambda equals 3 right there. You wouldn't normally do that. And then the 2 corresponds to this. So in some sense, it does tell me that I'm moving faster in this direction than I am just right at that moment. But I have source stuff coming out. And actually that'll help a little bit when we sketch, because we know we're tangent to the slow direction. And we become parallel to that one. Now that's not gonna last long. So in some ways the slow fast, it doesn't last long because these predictions are super local. Like the prediction for this one, I wouldn't go very far with it because things change fast as you move away, just like the weather, right? This is why we can't predict the weather. It's a non-linear model. Non-linear things are crazy. That's where the world is a non-linear thing. The world is a wonderfully non-linear, wiggly-ass thing to be in. Nothing we ever do in math really is the world, but it sure is fun to pretend. So this thing is just kind of outsourcing here. We know that much, that there's stuff just shooting out. That's gonna help when we get to the saddle because it tells me that the input part is probably like just right there on the saddle. And the other input part's always opposite that, so we'll get there in a second. Okay, so then at 3, 0, this guy, it's a sink. So that means I'm flowing into it. And I could go ahead, that one's got a complicated eigenvector, but I got this feeling, and you'll see why. I kind of got a feeling it's coming in from in right there, kind of. Right, because think about this. This is a saddle, right? So it's going to have an incoming, and that's going to be opposite, and it's going to have an outgoing, like that. Oh hell, why don't we just put it there? Anyway, because now I'm starting to piece it together. As you put these things together, every time you get a hint about something, see what it tells you about other things. So there's probably even a direct link between these two, a single path that leads there. And then what was 0, 2? Was that a sync?
Yeah.
Sync also. Look how consistent that is. This was a sync, this one's pushing into that, this one's pushing into a sync there. So there's also syncing on the other side. Pretty much about done. Notice how much perfect sense that makes here. This is an out direction, so I'm just gonna link it up here like that. And then I'm gonna create these points. There's always a fine line, a single solution that links all these things together. And now, once I've got the skeleton, let me stop. Make sure you understand how the skeleton was produced. Does it seem okay? Everything seem okay? Okay. Cool. Having you keep an eye on me. Now I've got to flesh out the rest, and this is all I know. So I try to make trajectories that do not intersect but are consistent with everything else. So these sinks, everything will flow into those sinks when it's nearby them. And now we've got a sense of how this population model rolls. I'm going to stop. You tell me if that's okay. This is one of my favorite. I think I say like this is one of my favorite things to do like every other day roughly. Sounds like me. The good news is I get to do some of my favorite things every other day on a life. Pretty good life. No bitching. You hear any of your professors bitching? Just slap them. Don't do that. Don't do drugs. Don't hit your professors. Yeah, some stuff happened in geometry last time, so I have to keep saying that. All right, there we go. We good? So now, we can predict the possible outcomes. What are the outcomes? What can happen to this population? Remember, this was the rabbits. This is the sheep. What are some stories about the pasture? We'll call this book The Pasture. A tale of sheep and rabbits. Somebody tell me one possible thing that can happen. There's like quite a few good stories to tell here. What happens if there are, 1 rabbit, 1,000 rabbits, and 500 sheep? That's about the 500 mark right there at the halfway.
Bye-bye sheep.
Bye-bye sheep. Yes, exactly. So if I'm here, so we can just, yeah, I like that. That's a good story. A nice, simple, lovely bedtime story for the children. So if x at 0, the original is 1, and y at 0 is a half, then x of t and y of t head towards, so the x goes to 3, but the y goes to 0 as t goes to infinity. Sheep win. Rabbits win. That's a W for the rabbits. L for the sheep. If I have a converse situation where I have 500 rabbits, but 1,000 sheep. What's the story, Lou?
Bye-bye rabbits.
Bye-bye rabbits. So if we have x at 0, let's just write a few of these things out, equals 0.5, y at 0 equals 1, then I'll just write that, bye-bye rabbits. Sheep win. What if I'm out here? What if I'm anywhere underneath this line right here? What happens to all those states? Rabbits win. Yeah, bye-bye. So, notice that this whole region, I need a new color, this whole region down here forms what's called a basin of attraction for that fixed point. Erstwhile, above that line, we have a basin of attraction for the sheep win. And I don't have many, I got a color up here, I got another color, I guess. So this basin up here is basin of attraction for 0, 2. You start in there, that's where you go as time unfolds. Is there any peaceful outcomes?
Right at 1-1.
Yeah, right at 1-1. So yeah, if we're right at 1-1, happy, 1,000 sheep, 1,000 rabbits, forever.
Or if there's no sheep or no rabbits at all.
Wait, say that again. Oh, yes. And if there never was a sheep or a rabbit in the field, that's also vacuously satisfied. So I'll say a word that I said to my geometry class. That was a vacuously satisfied sheep and rabbit population. They are satisfied as hell because they don't know any better, because they don't ever live. So, but there is a fine line here. There is a manifold, and I used this word before. There's a curve manifold leading to 1-1 on either side. And I'm going to just make that in red. It's really hard to find those. But there is this hairline situation. So if things land just right, if they were to be out here and just perfectly on that place, then they would head here and reach the equilibrium. But if they're off of that, man, the odds are really against one of the populations. So if you were placing bets on this, it's a 50-50, it's a crapshoot. You'd have to know information about who had the greater numbers really at the beginning. There we go. That's a linear portrait. Non-linear portrait, sorry. Things get weirder. I want to make a few comments about some of these predictions. Let's look at the tau delta. And then I'll call it, and we can hang out, and if you want to ask questions or work on those phase portraits that you have. I think I extended that extra credit assignment till just give it to me before the final. It's a lot. Lou and I were talking about it today, and it gets nitpicky. If you want to talk about it with me, if you're starting to get overwhelmed with it, talk to me, and I'll help you out, because there's a lot going on there. But let's look at the tau delta. So this is delta, this is tau. If you are inside this parabola, if you are here, or here, or here, or here, these, or even here, anywhere but these lines, those are called robust cases. So if I make a prediction that I'm in here, and I'm clearly in here, so I do the Jacobian. So if the Jacobian's eigenvalues land me in here or here, anywhere but these dang lines, I can trust that prediction. Robust, robust. Because we're taking something squiggly and we're pretending it's a line. But sometimes the nonlinear terms can create a false impression. So if you predict you're a center, you cannot be certain of that without further analysis. Because it's possible the nonlinearities really meant you were there or there, and those are pretty different situations. This is an unstable spiral. This is a stable spiral. So let's just make a little note. If we predict a center in a nonlinear system, not 100% guaranteed. Saddles, always guaranteed. If you predict a saddle, man, it's definitely a saddle. If you predict a stable node, or unstable node, unstable spiral, stable spiral, unstable node, those are all legit. All those predictions are 100% good. It's this case here that is precarious, and it is this case here that's precarious. And then I guess really this one here too. So if you land on one of those lines, things are, so if you land on a line in the tau delta plane, a dividing line. So in other words, when would that be? I.e., if tau squared equals 4 delta, in other words, tau squared minus 4 delta equals 0, or tau equals 0, or delta equals 0. These are sus, and you need to do further analysis. Does that all sound reasonable? So you've got stuff to work on. Who's done with the phase portraits for Monday? Well, you're kind of done, right? You just have to write a story.
Yeah.
Kind of okay. Cool. Let's take the last 20 minutes and work on those. And that way, if you haven't started, you should get started, and I can help you. And if you're already done and you don't want to do it, it's not that long. You have to wait. It's making me so damn happy. Anybody, you good? You need to chat or anything? Feeling good? Okay, cool, ladies. Okay, yeah. So how are you feeling on that? Oh my God, Cecil's gonna ask me a question. This is cool. Yeah, I'll keep you to just look at him and see how you. Okay. Yeah, if you haven't started number 3, that is a little more challenging. I guess, yeah, just you should look at that. I'm going to talk to Cecil about it here too, so maybe I'll say some stuff up on the board. Yes, so that all looks great. Yeah, that looks really good. I would add a few on this side, but that looks really beautiful. Yeah, very nice. Then this one turns out to be a center. Yeah, that looks great too. Just add a few more, but Yeah, the concentric. Yeah, yes, ma'am. Inside, mostly, just a couple more, no problem. So usually you kind of want to have a lot, at least a few trajectories shown to get the full fleshed out flow. Oh, sorry, I don't know what that is. Okay, well if you want to convert it to X and Y, it's really just what you've done. So, does that make sense?
Yeah.
Okay, yeah. Yeah, number 3 is in J and R, but if you want to call them Xavier and Yolanda or whatever, you know.
I have a question.
Oh, great.
So, at the beginning of class, you mentioned something about square root of 17.
That's on number 3.
Yeah, I didn't get that.
Let's take a look. Oh, maybe, yeah, let's check. I think it's square root of 17. So let's see. So 3, 1, 2, tau is 0, delta is definitely -5. So, I think it comes in when you do the eigenvectors. So let's take a look. Well, maybe, I don't know. Hey, Lou,
Yeah.
you got a square root of 17 on number 3 face portraits? Because I'm starting
It's
to
like-
wonder about that.
I ended up with that because you have to use the quadratic formula.
Yeah, yeah.
And then
Hmm.
that's what I did. It's like square root of 17 over 2.
Maybe can
It's
you
just
can you
that.
pull your work out really quick, please?
Yeah.
Because this looks pretty good to me. Ms. Lou, did you get a square root of 17? Or
Yeah,
you were
like
just
negative 1 minus square root of 17 over 2.
interesting? I don't know, because this looks totally right to me. I mean, are we doing it? I don't even know how you get. I honestly don't see where 17 would pop up in here. You took solar lambdas, square root of 5, you took it off, you got -2. I don't know, Evan, this looks okay to me. Yeah. This looks pretty good to me. I'm gonna go take a look at those square root of 17 ones. But yeah, if you had something else, yes.
I get the vectors. I'm just kind of confused about how I'm supposed to plot
Mm.
them.
Okay, so so can we go back to that previous page? So you did a good thing, you got a decimal approximation. So this one is like 1 over and then a quarter down, right? And let's see what we got over here. So that looks great to me. And then on that page, oh shoot, I screwed it up. I should have just let you do it. Hang on, it's that button. And that was the lambda is negative √5 one, is that correct? So just you have incoming, that's an attracting direction. So let's go back to, so you put an incoming arrow there on both sides. That's an attractor. And this will be a source because that's the positive eigenvalue.
And then I have to find some points in here to figure out what it's doing.
Yes, but you should also use the tau delta classifications.
Oh, that's right. Okay.
And that'll tell you what it is.
Okay.
But you've got all the details now, but don't forget to do the tau delta
Because
thing.
so this would be a saddle.
Yeah, exactly.
And, so it would just be something like a saddle.
Exactly, and and just fake it from there.
Okay, and for this one,
That's perfect.
and is there anything that like changes the size of the circle?
No, not really. Did you check the direction of
Yeah.
rotation? Cool. So I would just add a few more concentric circles and you're good.
Like just
Like another one. Yeah, always include a couple, like 2 to 3 trajectories. I would say 3 is a good number. Like an inner one and an outer one.
okay.
But that's perfect.
Alright. Cool.
Yeah, thank you. Cool. Lou, can you look at that root
Yeah.
17 thing? Because I'm
Yeah, I was just doing it. Otherwise, I've been using it's just to double check myself.
I trust you.
Yeah.
I know you're not
No,
letting the
but
computer do work.
no,
because
but I'm like, but yeah,
Um,
I got the same item. This is it was kind of a us.
Oh, wait, Evan, this is on number 3. That the square root of 17 appears.
Number 3.
There was third one, that's the relationship one with J and R. So I think that everything you, is that the one we were looking at?
Maybe I copied down the numbers.
Yeah, maybe.
What was the matrix?
Well, wait, actually,
Yeah,
what is
no,
your?
Because when you wrote it down,
Oh.
you flipped the J and R. I think to mess with
That's,
us.
I didn't do that to mess
Oh,
with
are
you.
you
I would
sure?
never-
I think it was to make sure we were
That's-
paying attention.
No. No, so let's talk about this, this is good, so Evan, so square root of 17 does sound right now. The J and the R, you've gotta keep them in the right order, so let's actually put this up for everybody to see. So it was,
Oh, yeah, I see that now.
see it, yeah, okay, so R dot, what was that, so I can just put it
It's
up?
negative 2R plus J. And then you wrote it as J plus 2R, but you can just flip them. So 2R plus J.
Yeah.
Is that what wait,
That's what you put up. You did J plus 2R for the J dot in the problem that you
Got
just
it.
did. So
got
then
it.
put in
It's
like
probably
an
not
easy
what I was,
matrix.
yeah, it's fine. I mean, it's what I got and people have been working on it. Katrina, is this what you did?
I haven't done that one yet, but I do see what they're talking about. And I see
Yeah.
how that could be confusing.
That could be confusing. I'm sorry about that, Evan. It was not intent. I would not try to fuck with people just like that.
Are you sure? Maybe a little
Sure.
extra over there?
So, yeah, so I guess. -2, 1, 2, 1. I guess I'm actually doing some of it here, huh? So our tau was -1, and then our delta is -4. So it is a saddle. Yeah, okay, cool. Yeah, and I looked at your portrait. I like the way that
Yeah.
worked out. Cool.
Okay.
Okay, yeah. Saddle for number 3.
I have a question for you.
Yes, sir.
So, is there a way for you to be able to calculate the paratonic fold?
Oh.
That's like. I was just
Yeah,
curious,
no,
'cause
it's,
looking at
I was
it.
wondering that while I was talking about it too.
If you don't know the answer, that's alright. I was just curious if you knew off the top of your head.
It's a neat question.
Because
I don't know of a way.
Kind of easy, but
It kind of does. Like, I don't think it's a line though. I think it's a
Okay.
weird curve.
okay.
Well, let's see. Let's see if it's a line. Let's just test that hypothesis. So, so if it was a line, it would be a line that x and y were equal on, right?
Yeah.
So x would, let's parameterize it. Let's assume that our solution looks like that, and yeah, right?
Yeah.
Yeah. So then x dot is 1, y dot is 1, and what was that actual equation? I don't.
The
quite-
original one?
Yeah, let's see, so it was, oh yeah, it's this guy, right?
3 minus x minus 2y. Yeah.
Yeah. Okay, so let's see if that's actually a solution to these guys. I feel like it's not going to be because it doesn't involve E. Yeah, let's be a little smarter on that. So we want, how about? So then when t is 0, I'm at 0, 0. Well, I can't leave there.
What if you did plus 1?
Yeah.
Oh, no, 'cause
Or
then
how
you're
about just
just-
plus a little,
Okay. Yeah.
just to get us.
Out of there, yeah.
Yeah, but then when t equals 0. Oh, so okay, so that'll be 1 at t equals 0. 2. How about that? No.
No, cause that's, I mean, it's in a neg, or no, yeah, oh. 'cause
One
that-
minus, what about that?
We just started with that.
Shit.
What if you did like 1.5?
Like 3 halves here?
Yeah.
Okay, let's see. So then when t equals 0, we're at a half-half.
Yeah.
And as t goes to infinity, we go to 3, we pass it. We go right through it, and that doesn't. What we need to definitely be approaching like that and then slowing down as we get there. Okay, so let's get an initial condition. So let's start at a half. And then the equation there would be a half. So x would equal half. And these are gonna be identical, so that's nice. Half plus. Let's use an e. Let's use an e with a negative t somehow, so that the thing shrinks to 0.
Yeah. Oh.
Okay, yeah, hold on, keep working. I'm just gonna make fast. Does anybody need help? Anybody have consultations? Okay, good. Not good. Well, it is good. But if you have one, don't let this get in your way. Oh. No. So we want this to be at most a half.
Don't we want it at most to be 1?
Oh, I mean, just the part we're adding on, sorry.
Oh,
This- the thing we're
yeah.
adding on, yeah. And we want it to go, oh, here, let's make a graph. So, let's see, so x and t. So we want 1 to be this asymptote. We want something that looks like that. Yeah?
Yeah.
Yeah. And we're starting at a half. So that is like 1 minus. That's it.
Yeah, that's it.
We'll see. We'll see. Okay, so then,
I'm not doing that too, cause did you get that to 7? So we have that cause they put it in there, cause that's like the third part, but it doesn't the center of the line.
I don't know, Lou. Well, shit, let's look at the y one and see if that's if it looks easier. So y equals. I might ask you to check this while I go, just see what's going on elsewhere. Could you check that for me, please?
Yeah.
Let me see. Everything okay over here? Anything consultations needed or anything?
I'm just wondering on the second one,
Yes or no?
that it's a 7,
Yes.
so do I not have to do this part then? Or just don't want us to do it, just cause you said it's.
Oh, yeah, I guess you don't really have to do 3. You definitely shouldn't do that, because,
I'm just gonna do that shit. I mean, we can
yeah,
still
don't do it. Yeah, please don't do it.
Okay.
The only thing you should worry about is the direction of rotation.
Okay.
Just test a vector.
Okay.
Yeah,
Okay.
cool. And that is the right answer. It is a center.
Okay.
Cool. Question?
Oh,
Oh, you just kind of talking. You weren't talking to me. Okay.
This is like this. Yeah. I did my nails. So maybe I did one. And I did the rest. Yeah.
think so.
No.
I don't think it's working out. It's turning out really neat. Like it's pretty, but it's not true. I almost think we need to maybe put an alpha in there so that the rate, because maybe the rate isn't, you know what I'm saying? Like
I
we
think
don't
so, yeah.
we don't know the exact velocity, and we're making a very strong assumption about it. And maybe if we put an alpha in there, so let's do that. So if we put an alpha in there to control the speed, then x dot would actually be, there would be an alpha there. And maybe that'll allow us to figure out what the alpha should be. No, and that's just one, right? So we need to figure out the alpha. Let's see.
I don't think so.
I don't either. Sure was fun to pretend though.
Yeah,
I don't think it's a straight line coming in,
that makes sense.
and yeah. So, I don't know the way off the top of my head.
I also was just kind of asking in general, like,
I think it's a really hard problem.
okay,
Yeah, it's like best left to a robot friend. Yeah,
fair enough.
or a researcher, or someone who wants to research something. I don't know. Oh, I was thinking about a research problem earlier that I was going to tell you about. I can't remember. If you're lost and thought it is quarter till, you don't have to leave. It's vapor. I thought of it earlier. I thought of you.
That's alright.
Maybe it'll come back, hopefully.
I had another question though.
Yes.
So if it falls on one of those lines that you don't like, on the tau delta graph, what do you do then?
Then.
Besides like cry because it doesn't work out.
Bye, have a good weekend. You too. Keep an eye out in your email about Monday and the eclipse, and we will have class, but we might start a little late. That would be it. Cause you gotta see the eclipse, right? See the shadows. What's that?
What are you doing if you don't?
Exactly, yeah, you're not living. You said
But you're
definitely not.
definitely not gonna see it in the next one. Catch it in 7 years.
You too.
So this is the extra credit one.
Oh, okay.
AR plus I, and that's minus PR.
How did this go to that?
That is what I was going to check in with you.
So this is right.
That's right.
This is not right.
Mhm.
That is not true unless A equals 0.
That, yep.
So you gotta work from here. Bye, Katrina. Have a good
Cause
weekend.
I was like, oh, yeah. Yeah.
Go ahead, you go ahead.
Yeah.
Does that make sense?
Yeah.
Yeah. And then from there, Lou, if b squared is bigger than a squared, then that's delta's positive, and you're in the upper half. If b squared is less than a squared, you get a saddle. And you're underneath. So you can use that as kind of a guideline for like some of the possible things that can happen. Does that make sense?
And for the phase plan,
Let me stop this
you just
recording.
act like numbers